Welcome back. We're going to continue our journey through our integration techniques, and we're in the midst of learning about trigonometric substitution. So remember in the last video, we formulated the idea of trig sub, where it comes from, our identities that we're going to be using, the types of scenarios we're going to be running into, sums or differences of squares, a is a constant, and maybe under a root specifically. And in those cases, when we run into algebraic expressions like this, it turns out that if we let x, our variable, be transformed into a trig function, so we replace x, the variable x, by a trig function, either sine, secant, or tangent, we can then transform an algebraic expression into a single trigonometric function. So we take an algebraic function, something complicated that doesn't simplify, and transform it into a very specific and a nice trigonometric function. And so we saw that both algebraically and geometrically in the last video, and now we're going to apply this to integration. We're going to take this knowledge, this trigonometry and substitution idea, and apply it to evaluating indefinite, and we'll also look at some definite integrals. And so the idea here is when we see a sum or difference of squares, preferably under a root, but it doesn't have to be. Look at this example here, where we can still use it. Sums or differences of squares in which we cannot evaluate it using U substitution or integration by parts, right? We want to go through all of our techniques, right? We want to think about all the things we've learned. But if those scenarios or those techniques don't help me, trig substitution is also a useful tool. So it's not a answer all for all types of integrals. It's only for certain types of scenarios. And we'll look at types of integrals that fall into these scenarios. So specifically, we'll look at this first example, the indefinite integral of the square root of 9 minus x squared, underneath the root. Now, if we look at this integral, we can't evaluate it directly because of the composition that we have, a function inside of another function. And unfortunately, U substitution doesn't help me either because we don't have a 2x multiplied outside of this integral, negative 2x. And so U substitution doesn't help me. Integration by parts maybe, but we only have one function. We would need to think of it as multiplied by 1, and then use that funny trick for integration by parts. So I'm kind of at a loss, but I realize, hey, this is a difference of squares underneath the root. If I replace that variable x by a certain trig function, it should give me a trig function that maybe I could possibly integrate, or a trigonometric integral that I can answer. And so if you look here, and remember we learned some shortcuts to kind of remember which trig function to use. Remember, trig sub, t or s, you're going to be either using sine, secant, or tangent. Those are our trig functions that start with t or s, sine, secant, or tangent. If it's a subtraction, you will use sine or secant. And then it depends on whether the constant is first or second. Remember, if the constant is second, secant, otherwise sine. If it's an addition of squares, a plus sign between the two, that looks like the letter t, and in that case, we're going to use tangent as our substitution function. So if we look here in this case, we have a subtraction of squares, difference of squares. So either sine or secant is going to be the correct choice of trig function. And in this case, the variable or the number comes first. And so that means it's not secant. If the number is second, secant. Number is first, well, then it's sine. And so the trig function that I will use in the substitution is sine. So I'm going to replace x with sine of theta, but we're going to need a constant in front. Remember, it depends on what this constant is. In general, it's a square, right? And so I'm not going to put 9 sine theta here. Instead, I'm going to put 3 sine theta, the square root of that number. That way, when I square 3, I will get 9, and then we could factor it out and do the whole thing we did in the last video. That's great for the algebraic part. Now, when we apply this to integration, it's always important to remember that there are 2 parts to any substitution when it comes to integrals. There is your function replacement, your either U replacement in U sub, or your X replacement here with trig sub. And then there's always your differential replacement, your du replacement, or in this case, your dx replacement. Right? We always have 2 parts, a function and its differential. A height and a base to a rectangle if it's a definite integral. And so 2 parts to my substitution as well, right? We didn't do it here because, well, we weren't doing calculus. Now we're applying it to integrals, and so if that's the substitution I want to make for x, then I also need to replace dx. So we need to know our derivatives of trig functions. Specifically, you're going to need to know the derivative of sine, the derivative of tangent, and the derivative of secant. In this case, the derivative of 3 sine of theta will be 3 cosine of theta d theta. Now we're not making sure we have it because we're actually replacing x itself by this. So dx will just get replaced by 3 cosine theta d theta, creating a new differential form in terms of the trig function. So we'll do the substitution directly out, and we'll get a new integral, a trigonometric integral. Now, while you could go through the whole process of replacing x with 3 sine of theta, squaring in, factoring out the 9, using this identity, and getting a trigonometric expression, we already did it 2 times over in the last video, and so we know what's going to happen. If I have an expression that looks like this, and I replace x with a sine of theta, this expression will become a cosine of theta. So when I do this substitution, the whole point of doing it is so that this expression underneath this root simply becomes now 3 cosine of theta. So we get 3 cosine of theta. This expression here, I'll underline it in green, becomes 3 cosine of theta. That's what we have, right? A is 3 in this case. Now, of course, that's the algebraic substitution. That's our function replacement. We also need to remember not to forget our differential replacement, right? So dx. Dx needs to get replaced by, well, in this case, another 3 cosine of theta d theta. So we don't want to get confused. One of the 3 cosines of theta comes from the substitution. The other one comes from the differential that needs to get replaced, right? That's the dx part. So the algebra gives me this. The differential now gives me this. And so what do we have as a whole? Well, it looks like we get 9, which I can factor out, 3 times 3, and cosine squared theta d theta. And so what we need to do is be able to answer the antiderivative of 9 cosine squared theta d theta. Now, this is where it becomes useful, what we learned in the previous section, 8.3, or trigonometric integrals. Because now we look here, we're like, okay, I have a new trigonometric integral that I need to answer. It turns out that I have even powers of cosine. This is what I'm going to end up with. And so in that case, I can't evaluate this directly. I go back to the previous videos. I remember, oh, in this case, I use a half angle identity. And so if I'm using my half angle identity, I remember that cosine squared theta gets replaced with 1 plus cosine of 2 theta over 2 d theta. Using my half angle, right? We don't have, if we had an odd positive power, we'd pull one out and do a U sub. In this case, it's only even. I'll use my half angle identities. That 1/2 can be pulled out, so I'm not worried about the 2 in the denominator. And in this case, we can actually evaluate it directly. And we can now evaluate this integral directly, 9/2. Antiderivative of 1 is theta. Remember, we're in the theta variable now. Plus sine of 2 theta over 2 plus c. And so we evaluated the indefinite integral. And while we evaluate it, remember, this is now applying to integration, we have an answer, but it's like when we do u sub, you have an answer in terms of u, you need an answer in terms of your original variable, x. In this case, I have my answer in terms of theta. I need my answer in terms of x. And so now we would need to back substitute. Now back substitution becomes a little bit more difficult here because I need to replace theta by what it is in terms of x, which isn't explicitly written here as you have with u substitution. So in this case, we need to do a little bit of algebra and trigonometry to solve this for theta. I would divide both sides by 3. And then to solve for theta, sine is a function, right? It's not a number. We don't divide both sides by sine. We would need to take its inverse function. So remember back to Calc 1, we talked about inverse trig. And so we would need to take inverse trig of both sides. And so we would have arc sine of x over 3 is theta. And so now I can back substitute. Now I have theta in terms of x. Now the answer doesn't look very nice, but it is an answer nonetheless. So we have 9/2. Theta is replaced with arc sine of x over 3 plus sine of 2 theta. So 2 arc sines of x over 3 over 2 plus c. And so the answer doesn't look nice, but it is the answer. We'll talk about scenarios where we can make the answer look a little bit better, but in this case, this is fine. This is correct. This is the trigonometric answer to this question. What is the antiderivative of the square root of 9 minus x squared? It can be written as this trig expression. That's 9/2 times arc sine of x over 3 plus sine of 2 arc sines of x over 3 over 2 plus c. So using our trig substitution, doing the proper replacement, creating for ourselves a trigonometric integral, and then using what we know about trigonometry and trigonometric integrals to get our answer. And then the only thing would be, in this case, since it's indefinite, we need to do a back substitution. It becomes a little bit more, not more complicated, but just a little bit more work needs to be done, right? We need to solve this for theta to write it in terms of x, and then we can do it. It's not going to be a nice answer. Typically, will then involve inverse trig in my answer, but it is an answer. It is the antiderivative. And so let's do another one. Let's put it into practice again. So in this case, we have a sum of squares in the bottom. Now, it's not under a root, but I could still do trigonometric substitution. It doesn't have to be under a root. It's just nice if it does, because then it just becomes a single trig function. If it's not under the root, just realize square both sides, and that means a sum of squares becomes a squared secant squared. A difference of squares in this way becomes a squared cosine squared. A difference of squares here becomes a squared tangent squared. And so whether or not it's under a root is irrelevant. It's nice because then it becomes a single trig function. Otherwise, it's the square of the trig function. Just square both sides. And so in this case, we have a sum of squares. Now, when we have a plus sign, that looks like the letter t. And so that tells me I'm going to use tangent as my substitution function. I'm going to replace x by tangent of theta. And here specifically 4 tangent of theta, right? In this case, my a is 4. Remember, standard is a squared here, right? So if it's 16, that means a is 4. Just like here, 9, so a is 3. Square root of that number. And again, just like with any substitution, when it comes to integration, we also need to replace the differential. So it's not just enough to do algebra here. We need some calculus, some derivatives. And the derivative of tangent, remember, is secant squared. So we're going to actually replace dx by 4 secant squared theta d theta, the derivative of tangent. And so if I do this substitution directly, I get a new integral. What does my function become? 1 over, the whole point is an expression like this. A sum of squares becomes a secant of theta. Now, it's not under the root, so just square it, meaning that this will now become a squared secant squared. So this expression will become 16 tangent squared. Or sorry, 16 secant squared. Right, this expression will become a squared secant squared. So in this case, 16 secant squared. Sum of squares becomes this. And it's squared, right? Remember, it's not under the root, so that's why. Now, don't forget, right, that's my function part. That's what this expression became in the bottom. The dx also needs to get replaced by a 4 secant squared. And actually, since that secant squared is in the denominator and the other one's in the numerator, that actually gives me something very nice here. Because in this case now, the secant squareds end up canceling each other. Here they didn't cancel, right, because I had both of them in the numerator, so they just doubled up and squared it. What's needed? I needed to do some integration. In this case, they cancel, and everything cancels then except for a constant, 4 over 16, which reduces to 1/4 d theta. Well, that means my integral is now 1/4 theta plus c, antiderivative constant. No technique of special tool here for this integration. But then again, just like any substitution, now we need to back substitute. So here, we would need to replace theta by what it is in terms of x. Now, it's not solved for it explicitly, so you have to do a little bit more work. Tangent of theta is x over 4. So then theta is arc tangent, the inverse of tangent of x over 4. And so what's my answer? 1/4 arc tangent of x over 4. Let's see. So again, using our techniques or our trig substitution to transform it into a trig integral. In this case, the trig integral I get is actually just a constant, which makes it actually very nice. In fact, there were no trig functions left to integrate. That doesn't always happen, right? It didn't happen in the first one, it happened in this one. So it's not always that we're going to have to do something complicated when it comes to trig integrals. They could end up quite easy, and that's the benefit of trig substitution. Something starts out looking complicated, becomes quite easy. So let's do a couple more, get some more practice in. So again, similar type of scenario, we have a difference of squares, and it's in the bottom or in the denominator, it's under a root. I'm going to use trig sub here because it's a subtraction. I'm either using sine or secant. In this case, again, sine, because the constant is first. And so in this case, x is, and actually our number is just 1, right? So our a is 1, and so we're just going to do sine of theta. Again, we always need to replace our differential. The derivative of sine is cosine of theta d theta. And so we do our trig substitution. Now I put some other things in this integral as well. Remember that the whole point of doing this was that so that that bottom expression here transforms into a cosine of theta. In this case, a is 1, so we actually just get cosine of theta in the bottom. That's our function replacement. Our differential also needs to get replaced and become cosine of theta d theta. That's my dx replacement that needs to happen. And in this case, I threw some other things in the integral. I threw an x cubed in the numerator. Well, that's okay, right? Everywhere I've seen x, it gets replaced by sine. And so that means now in the numerator, it's sine cubed theta. That's okay. Now, before we attempt to solve this, let's simplify it. The cosines cancel, leaving me with the indefinite integral of sine cubed theta d theta. And again, we're back to looking at previous videos and learning how to solve trigonometric integrals. We have an odd positive power, so I'll employ the u sub technique from 8.3. I'll set aside one of the signs. I will take that sine squared and rewrite it using my Pythagorean identity as 1 minus cosine squared. I will now do a u substitution with this trigonometric integral. So u is cosine of theta, du is negative sine of theta d theta, so we need the negative sign, double negative. And we end up with a polynomial. So what we end up with is negative indefinite integral 1 minus u squared and du. Negative sine theta d theta becomes my new du. Taking the antiderivative and distributing the negative, we get negative u plus u cubed over 3 plus c. And now we're at the point where we actually answered the indefinite integral. We have an answer, it's just not in the right variable. So first let's replace u by what it is. U is cosine of theta. That's great. But that's actually still not the right answer because theta was also a substitution variable. And what is theta in terms of now x? Well, we would have to go back here and replace theta by arc sine of x, right? If I solve this for theta, taking arc sine of both sides, get this. And so we get negative cosine of arc sine of x plus cosine cubed of arc sine of x over 3 plus c. And again, this the answer doesn't look very nice, but it's the answer nonetheless, right? We have to do double back substitution because we did a u sub and a trig sub. And if we walk forward in the steps again, right, we had this expression. We have a difference of squares under a root, so we use the appropriate trig substitution, transforming this expression into a trig function. The remainder of the integral also needs to get substituted for, so we have this. We simplify it, we end up with a trigonometric integral that we can now answer. We answer the trigonometric integral, we back substitute to get my answer to the indefinite integral we started with. Now this answer doesn't look nice, and so now I'm going to try to rewrite this and make it look a little cleaner. Just give you another way to write your answers. This is completely correct. It's not incorrect. There's nothing wrong with this answer. It doesn't look nice, especially if I had to plug things in. Maybe not the best way to plug in 0 or x or something, unless you love inverse trig, and then you can go ahead and plug values of x in. But say I wanted to make my answer look a little cleaner, what I can do is use the techniques of geometry and draw some right triangles. So you remember back at the beginning of 8.4 when we introduced trig sub, we showed these identities and these relationships via a right triangle as well. And so that trig sub that I did here, the x equals sine of theta, can also be expressed as a trigonometric relationship. The fact that I say sine of theta is x gives me those two sides of a right triangle. Sine is opposite over hypotenuse. So if sine of theta is x over 1, then the opposite side of this triangle is x. The hypotenuse is 1. And sure enough, the missing side is the square root of 1 minus x squared. Right? The geometric relationship of this substitution. That's why we use that trig function for that expression. Why do I care about this? Well, if you remember our answer now, in terms of the trig function, now just relies on the ability for me to know cosine of theta twice over. Well, if this is my triangle for this pattern or this relationship, you can tell me cosine of theta without having to do a back substitution. You can tell me cosine of theta in terms of x. Cosine is adjacent over hypotenuse. And so actually going and using this relationship, I can rewrite the answer a little bit differently. We can write it as negative cosine of theta is adjacent over hypotenuse. Negative square root of 1 minus x squared. Adjacent over hypotenuse over 1. Plus 1/3, I'll put the 1/3 in front, and then cosine cubed. Well, then that's just the square root of 1 minus x squared cubed. Right, cosine is adjacent over hypotenuse. I'm cubing cosine, so cubing this expression, and then plus c. So both of these answers are correct. The cosine of arcsine 1 and also this expression. This is like the trigonometric version of my answer, and this is its algebraic counterpart. Both are the same. Both will give you the correct answer. There's nothing wrong with either. This is just a little bit cleaner. This is cleaner, of course, if I need to plug in bounds for x. It's a little bit easier than thinking about inverse trig. So using geometry, we can sometimes change the way our answers look to make them look a little nicer, right? Anytime you define a trig sub, this type of relationship, you are in effect drawing a triangle. The missing side of that triangle will be the expression in question, the one you start with in the integral. And therefore, if your answer is in terms of cosine of that angle, or sine, or tangent, or who cares, all you need to then is relate two sides of that right triangle, giving you a nicer answer, a cleaner answer. All right. And so let's do it one more time. Let's finally introduce secant, get an answer. Now, I will say, of course, in this example, you technically do not need trig sub. In fact, I would not use trig sub if I didn't have to in real life. Right? But since we're in the section of trig sub, I will use it here. But realize that I can actually use u sub here. We have composition, yes. We have a difference of squares under a root. But the derivative of what's inside of this root actually is multiplied in. I can write a 2x here, and we could actually do a u sub. But pretending I didn't see it, and since we're in trig sub, I will go ahead and use trig substitution. In this case, we have a subtraction, so sine or secant. The number is second, so actually I'm going to use secant this time. Secant of theta. And so that means dx is the derivative of secant, which is secant theta tangent theta. That's the derivative of secant. Doing my substitution, the whole point again of doing the substitution is because this algebraic expression then, that root, difference of squares, becomes, oh sorry, we need to put a 2 in front. And my a is 2. So that algebraic expression, the denominator becomes simply 2 tangent of theta. That's what the denominator becomes. Now there's more to this integral, right? There's some other things in it. We have an x in the numerator, so that means I need a 2 secant of theta in the numerator. And then the dx, right? We also have to do our differential replacement, right? Dx needs to get replaced by 2 secant theta tangent theta. And so that's my differential replacement, my algebraic thing that I did, right? The reason I chose that trig function, and then the other x in the numerator that needs to get replaced. Again, before we evaluate it, let's go ahead and simplify. I can cancel the 2 and the tangent, leaving me with still a 2 here, which we can factor out, and then a secant and a secant, so secant squared. So we get a trig integral. However, this is a nice trigonometric integral because the antiderivative secant squared we can evaluate directly. In fact, that's tangent. 2 tangent of theta plus c. And so we have a trigonometric answer. Antiderivative of secant squared is tangent. Now, of course, we need to back substitute, right? So in this case, we would divide both sides by 2. And then that means theta is arc secant of x over 2. And so I'd go back down here and I'd write my answer as 2 tangent of arc secant of x over 2 plus c. Replacing theta by arc secant of x over 2. And while that's a great answer and perfectly fine, box it and move on our way. I'm going to clean it up a little bit. I'm going to write an algebraic counterpart because I want you to remember, like I said at the beginning of this problem, you actually don't need trig sub. You can get an answer with u sub. And of course, u sub is not going to give you a trig answer. It's going to give you an algebraic one. And so how can I rewrite this answer? Well, let's draw a triangle. When I said that x is 2 secant of theta, I'm saying that secant of theta is x over 2, meaning when I draw a right triangle with the angle theta, secant is hypotenuse over adjacent, so secant of theta is x over 2. The missing side of this triangle is, of course, that's the whole point of the substitution, going to be the square root of x squared minus 4 if you do Pythagorean's theorem. And then remember my answer is tangent of theta. Tangent is opposite over adjacent, so tangent of theta is this expression over 2. So rewriting this answer here, the answer is 2 tangent of theta. Tangent of theta is then algebraically the square root of x squared minus 4 over 2. Now the 2's cancel, and you actually get a very nice, clean algebraic answer as the square root of x squared minus 4 plus c. These are the same answer. They're no different. A computer would not be able to tell the difference between these two because they are the same. So we're not trying to say that one answer is better than the other. It's just a different version of it. This one's nicer if I had to use it to evaluate things, right? If this was a definite integral, I may want to write it this way as opposed to this way. But if it's indefinite, it doesn't matter. We can leave it as either. And so again, just rewriting answers sometimes to make them look a little bit better. And so the last thing we're going to do, we'll do one more example of trigonometric substitution. And the only thing that we're going to do in this example is we are going to do a definite integral. The only thing that's an addition, as opposed to what we've been doing, is now taking that antiderivative, not putting a plus c on it, and plugging in some bounds. So let's do one more. Let's evaluate between -1 and 1, the square root of 1 minus x squared dx. So similar to the first one we did, but now a definite integral. And so similar to the first one, remember the first one, x is going to be 1, a is 1 sine of theta. So dx is cosine of theta d theta. Doing my substitution, the whole point is that this expression will become a cosine of theta. And so doing my substitution, we get 1 cosine of theta. The dx gets replaced by cosine of theta d theta. So we're going to end up with a cosine squared theta. And then we do need to change our bounds. This is important. And so I am going to change my bounds. Remember, when x is -1, we need a theta bound, and when x is 1, we need a theta bound. So what is theta in the first case? Theta is arcsine of -1. In the second case, theta is arcsine of 1. Now, both of these are nice numbers. Remember, arcsine means sine of what angle gives me 1, sine of what angle gives me -1. Now, sine is periodic, so there's lots of answers in general to sine of theta is 1. Sine of theta is 1 in a lot of places for a lot of angles. Sine of theta is equal to -1 in a lot of places for a lot of angles. But remember, arcsine, we limited the domain of these so that we get just one definitive answer. And if you remember back to trigonometry, arcsine of -1 has one very specific angle, and that would be -pi/2. Remember, we're limited to quadrant 4 and quadrant 1. If we want to talk about when sine of theta is equal to 1, arcsine of 1, that would be at pi/2. Remember some trigonometry. And so we're going from -pi/2 to pi/2. Change our bounds. -1 is now the theta bound of -pi/2, and 1 for the x bound is now my theta bound of pi/2. And so we get a definite integral, trig integral from -pi/2 to pi/2 of cosine squared theta d theta. And again, we imply or use all of our techniques from previous sections. So even powers of cosine again. So we have to use our half angle identities. Remember, my half angle identity is going to give me, we're not doing a substitution, a calculus substitution, so it's just direct, it's an identity, so I don't need to change the bounds. It's going to be 1 plus cosine of 2 theta over 2. So I'll pull out the 1/2. Definite integral minus pi/2 to pi/2, 1 plus cosine of 2 theta. And now we can integrate directly 1/2 theta plus sine of 2 theta over 2. And now the only difference is, instead of back substituting and putting in a plus c, now we're going to take this and substitute in my bounds, right? The fundamental theorem of calculus kicks in, says take that antiderivative, plug in pi/2, minus take that antiderivative, plug in -pi/2. 1/2 pi/2 plus, okay, sine of 2 times pi/2. This is important, right? We're multiplying by 2 here, right? We've doubled the angle. And so when I replace theta by pi/2, the 2's cancel, I end up with sine of pi. Now sine of pi is actually 0. So that second term's gone. Minus, now we stop to plug in 1, -pi/2, so we get -pi/2 plus sine of -pi, right? Because the 2's will cancel when I replace it. Well, sine of -pi is also still 0. So that second term's gone here as well. Now we don't get 0 for an answer because we have a double negative here, so be careful. We're going to get, what, a 1/4 pi here, plus another 1/4 pi. 1/4 pi plus 1/4 pi is 1/2 pi, so pi/2. What is my answer? Pi/2. Now, if you're really into geometry, you can actually get this answer a lot faster. If you're really clever, you would realize that the function I gave you is a semicircle. That would be like outsmarting me at this point. You'd realize, wait a minute, if I drew this function is a semicircle. You asked me to find the area under this curve between -1 and 1. Well, those are the bounds of this semicircle. So that's just half of a circle. So that would be half of pi r squared, right? Half of the circle, the area of the circle. What's my radius of the circle? 1. So that's half of pi 1 squared. Or, well, 1 squared is 1, so half of pi, or pi/2. And look, I got the answer in 3 lines as opposed to this whole integration, and that's just outsmarting me and using some geometry and the fact that I gave you a semicircle. Sometimes you don't want to overwork ourselves. Nonetheless, it's good practice. And so this illustrates again Trig substitution just applies to definite integrals. Again, the only other step is, of course, taking that antiderivative, and instead of back substituting and putting a plus c, we put in some bounds using the fundamental theorem of calculus. All right, so that will wrap up 8.4, trig substitution, and then we just have one more technique of integration, which we will introduce, called partial fraction decomposition in the next videos.